this case study, a buck power supply development kit is used as a platform for an example buck converter. A bench supply provides bulk power to the kit at 9.2 volts with a 3 amp current limit. The buck supply regulates the output at 2.0 volts into a test load. For the first exercise, we're going to look at using a very fast open loop sequence to make a large set point change. To review, let's look at the out-of-the-box demo in closed loop and a second compensator created in a previous case study also operating closed loop. Here is the out-of-the-box demo in closed loop. The top trace is the scope trigger, the next trace is the PWM timer pulses, basically the plant input. The next trace is the buck converter output voltage, and the bottom trace is a current probe point in the evaluation kit. Each pulse represents one 5 microsecond cycle. And here is the open loop sequence. We zoomed in a bit so that we can see the action, so there's a horizontal scale change. This is now 40 microseconds. If we used the same scale, the step would be even more vertical here. All of this assumes that such a rapid step change does not violate any system design goals or constraints. This sequence was generated using an automated procedure that ran in system on the target hardware. This is all well and good until you decide to create the compensator and run it closed loop. Now the fun begins. You will have one compensator for startup and another compensator that gives acceptable transient response after the system is on set point. Having two different compensators and switching on the fly is not a big deal. That's one of the advantages of digital compensators. We are not stuck with one and only one compensator. We could have many compensators already built and ready to use depending upon the conditions of the moment. So, for simplicity, I would suggest using the open loop sequence to get close to the set point, initialize the compensator error history and output history, and then regulate closed loop going forward from there. This would be a very nice solution, very practical, sensible, and easy to implement. These kinds of hybrid systems, where we mix open loop and closed loop operation, are generally a practical way to achieve desired performance under specific conditions, assuming the load is known and the set point step is known and the system is not changing. This can be especially useful if we want to squeeze every bit of performance from our system. On the other hand, if the load can be anything, or the set point step can be anything, or the system can change, then open loop operation is not practical. A robust compensator that always works under all possible conditions is the sensible approach. Moving on to the next exercise, let's look at using a very fast open loop sequence to make a small set point change. We zoomed in a bit so we can see the action. We can see here a larger initial pulse to get the system moving quickly. As with the large set point change, this sequence was generated using an automated procedure that ran in system on the target hardware. For this implementation, we could be regulating at V1 here, stop regulating and insert the open loop sequence, initialize the compensator, and continue regulating at V2 here, all done seamlessly. That would be easy. However, for this exercise, we're going to do it the hard way. We're going to attempt to build a compensator that generates the required plant input that produces this plant output. Bear in mind that when we are building a compensator, we are actually building an approximation of the ideal compensator, which may have many coefficients. Depending upon the speed of the processor and the sampling rate of the system, we may find ourselves short on time if there are too many computations to be made in each cycle. In this system, we are running a 90 MHz processor and a sample rate of 5 microseconds. Sometimes we get lucky and a compensator approximation using only a few coefficients matches the ideal compensator well. Sometimes we're not so lucky and the approximation is not as good as we would like. Generally, the more coefficients, the better the approximation and the greater the computational complexity. These are the trade-offs that need to be evaluated in every system design. Also, I start to feel uncomfortable if we get too crazy with the number of coefficients. There is system noise and imperfections in the feedback measurement, so errors can creep into the computation and start to negatively impact the result. It's the old saying, garbage in, garbage out. So we have our plant input sequence and output sequence, and we end up choosing a compensator with 12 numerator coefficients, 3 denominator coefficients, plus the integrator. How did we do? Here is the result. Using the 12 by 3 compensator just designed, we are operating closed loop at V1, here, abruptly change the set point to V2, here, and we continue operating closed loop through the set point step change. Not too bad, but not perfect. If everything was perfect, we would have less to talk about. So let's talk about it. What's going on here? Let's go back and look at the compensator. Here we see the ideal compensator in blue and the approximation in red. Actually, 12 and 3 gives a pretty darn good approximation. In fact, you can see that the red pretty much overlays the blue here, and then we just start to see a little bit of blue creeping out from underneath the red over here. So it's likely that system noise or measurement error is starting to give us some grief. To really dig into it further, we would have to capture the compensator action in real time and examine the computations step by step. Then we would know for sure exactly why it's not perfect. Now, would I consider deploying this compensator in a released design? Absolutely not. This is a ridiculously aggressive compensator designed as an exercise to see what is possible in the extreme. For comparison, here's how the out-of-the-box compensator performs under the same conditions. This compensator uses 3 numerator and 1 denominator coefficients plus the integrator. Moving on to exercise 3, we're now going to consider a scheme that uses advanced notice of a known load change to completely eliminate the disturbance at the output. The idea is to proactively get out in front of the load change instead of responding to the disturbance after it already happened. What we're going to do is create an open loop sequence in system that adds custom PWM cycles that are exactly synchronized with the known load change to cancel out the output disturbance. Before the load step change, we will be regulating using a safe compensator that is not overly aggressive. When we receive notice of the upcoming step change, we temporarily suspend closed loop operation, insert the custom PWM cycles into the plant input sequence, initialize the compensator error history to zeros, initialize the compensator output history to the final PWM value, and resume closed loop operation. How did we do? Here are the results. When I first started working on this idea, I expected the disturbance to be smaller. I had no idea that we could do this well. The disturbance is essentially imperceptible. We can see the change in the inductor current here, so we know that it's really working. Well, we had fun exploring open loop standalone sequences and also open loop sequences used in combination with closed loop operation to create interesting high-performance solution. This concludes today's video. Thanks for watching.